Okay, boleh rekod Okay, class. Assalamualaikum warahmatullahi wabarakatuh and good evening. So I will continue our lesson on the properties of Laplace transform. So we already seen two properties of Laplace transform. The first one is linear properties, and then second one is first shift properties. So this is the first shift properties, which is you multiply a function ft with exponent at. So today I will continue our lesson with the third properties. Let me see. Okay, so this is the last properties for Laplace transform. We call multiplying by Tn. So let's see theorem 4.3. Given Tn, t to the power of n, with n equal to 1, 2, 3, and if we have a Laplace transform of function ft equal to fs, then a Laplace transform of function Tn multiplied by function ft equal to -1 to the power of n d to the power of n over dsn time Laplace transform. So what does this property mean? So let's see. Let me open a blank page. So let's say we have a function Tn where n equal to 1, 2, 3, and so on, whatever n. And we have a function ft. We know that by using Laplace transform, so if we transform function ft, so by using Laplace transform, you will get fs. So apply Laplace transform on ft. So Laplace transform of ft, which you get fs. So fs is the function in S domain. We call the Laplace transform of ft. Now let's say we want to find if we have a function Tn multiplied by a function t. Just now we know that if we transform this ft, you got fs. So what happened if we have function Tn? For example, t to the power of 2 or t squared multiplied by ft. You already know what is Laplace transform in ft, which is fs. So if I apply a Laplace transform for any t with the power n multiplied by ft, what I need to do is, first, this is equal to -1 to the power of n. So if n is odd numbers, you will get -1. So if odd, you get -1. Or if n is even numbers, even is 2, 4, 6, and so on. So -1 with the power of even will get positive. So this is equal to -1 to the power of n. Differentiation of function s with respect to n over s. D to the power of n over ds to the power of n, where you need to differentiate a function of fs. So fs is a Laplace transform of ft. So let's see one example. So find a Laplace transform of ft equal to t exponent et. So original, we have function ft equal to t exponent t. So now identify what is t to the power of n and what is ft. So here we have this t. Actually, this is t to the power of n. And let this et be a function ft, which is not this function. Another function we call ft. So in order to find the Laplace transform of t exponent t, first we need to transform this exponent t. So let we have ft. So a Laplace transform of ft, this is equal to, you apply a Laplace transform of ft to the power exponent t. So Laplace of exponent t. So referring the Laplace table, I hope you open your book. If you have a book or you have a note, see where is the table of exponent t. So exponent t is 1 over s minus 1. So this is equal to fs. So Laplace transform of exponent t is 1 over s1. So if we want to find a Laplace transform of t multiply ft, so by using this theorem, because n is 1, so negative 1 to the power of 1 d over ds. That means only first order differential equation. So first order differentiation of fs, where our fs is 1 over s minus 1. So what you have now is, you need to differentiate this function. After you get the value of differentiation, first order differentiation function, you must multiply with negative 1. This is equal to negative 1. So let's differentiate this function first. So we have 1 over s minus 1, or I can also write this as s minus 1 to the power negative 1. So if I want to differentiate first order, so let's rewrite negative 1 first, and then the differentiation of 1 over s minus 1. So by using chain rule, I get negative 1 s minus 1. So negative 1 minus 1, and then differentiate s. So s is s to the power 1, so you get 1. So close the bracket. So here you get negative 1 multiplied negative 1 s minus 1 negative 2. So negative and negative will be positive. S negative 2, you can rewrite as s minus 1 to the power of 2. So this is our transformation, Laplace transformation, by using the third properties, multiply by to the power of t to the power of n. Another example. Okay, another example. T squared, find the Laplace transform of t squared exponent minus 3. So here we have t to the power of n, where n is 2. And ft is exponent negative 3t. So let's rewrite this one. let this function equal to ft. So t squared exponent minus 3t. First, we find the Laplace transformation of fs. So we want to find the Laplace transformation of exponent negative 3t. So let's rewrite this one as fs equal to Laplace transformation of exponent minus 3t. So by referring table, this one is s minus minus 3, so s plus 3. And then by applying the theorem, multiplying by Tn, so if we want to find a Laplace transformation of t squared of exponent minus 3t, so this one is equal to negative 1 to the power of 2 d squared over ds squared fs, where our fs is s plus 3. So now you see that for n equal to 2, you need to differentiate 2 times to get d squared over ds squared. So first, you differentiate this one. After you get the function, you differentiate second time. So you need to differentiate 2 times. So let's rewrite this function. So 1 over s plus 3, you also can rewrite as s plus 3 to the power of negative 1. Negative 1 squared, so will be positive 1. So first, ds, that means you need to differentiate this function first. So differentiate a first function, this one. So what you get is negative 1 s plus 3, negative 1 minus 1, and then differentiate s. Sorry, so negative 1 minus 1, and then differentiate s equal to 1. So this one is differentiation of negative 1 s plus 3 negative 2. And then you differentiate second time. So you have negative 1 multiplied negative 2 s plus 3 negative 2 minus 1 times differentiation of s plus 3, so equal to 1. So negative 1 times negative 2, positive 2, times s plus 3 negative 3. Or this one can be rewrite as 2 over s plus 3 to the power of 3. So you see that by using this theorem, if you have n greater than 2, that means you need to differentiate 2 times. If you have n equal to 2, you need to differentiate 2 times. So you need to differentiate for second order. If you have n equal to 3, you need to differentiate up to third order. If n equal to 4, fourth order, and so on. So this theorem, it's quite difficult because you need to differentiate according to n, to the value of n. Okay, let's see one more problem. Find the t cos 2n. So our function, let's say ft equal to t cos 2t, t cos 2t. So here we have n equal to 1, that means you need only to differentiate for 1 times only. So you need to differentiate only 1 time. First, let's transform our ft first, cos 2t. So transform cos 2t. So Laplace transformations of cos 2t. So this is equal to s over s squared plus 2 squared, or s over s squared plus 4. This is Fs. And then to find a Laplace transformation of t cos 2t, so because n equal to 1, so negative 1 to the power of 1. So first order only, differentiate of s over s squared plus 4. So here we have to differentiate s over s squared plus 4. So this is differentiation by using product rule. So let's the numerator equal to u, denominator equal to v. So by using product rule, you have v du minus u dv over v square. This is the formula for product rule. Not product rule, quotient rule. Sorry. If you have a fraction, you use quotient rule. So u is s, v is s squared plus 4. So we need to differentiate only one time. And don't forget to multiply with negative 1. Right. So first, the numerator, the denominator is v squared. So let's write v squared s squared plus 4 to the power of 2. v du. So v is s squared plus 4 du, differentiate s. So you get 1. U is s, differentiate dv. So we get 2s. So s squared plus 4 multiply 1 minus s times 2s. So expand this one. So we have negative outside. So s squared plus 4 minus 2s squared over s squared plus 4 squared. So s squared minus 2s squared, so minus. So we have minus s squared plus 4 over s squared plus 4 squared. So multiply with negative 1, so you have s squared minus 4 over s squared plus 4 squared. So this one is easy lah, because we only have first order differentiation, because n equal to 1. Alright, I think this is last one. T squared sine t. Yeah? So we have a function t squared sine t. So let's say this is ft. So first we want to find a Laplace of t squared sine t. So first we transform sine t. So Fs, let's define Fs as a transformations of sine t. So sine we have net minus 1 squared. Then this one will be 1. 1 over s squared minus 1. And then apply the theorem. So Laplace transformation of t squared sine t. This is equal to negative 1 square d squared over ds squared 1 over s squared minus 1. So you need to differentiate 2 times. You need to find the second order of 1 over s squared minus 1. So we have 1 over s squared minus 1. So let's rewrite this function as s squared minus 1 minus 1. So differentiate first time. Minus 1 squared is positive 1. So we have d over ds. So first time you differentiate, you get minus 1. S squared minus 1. Minus 1 minus 1 is minus 2. Then differentiate s squared, so we get 2s. So we have d over ds times negative 2s s squared minus 1 to the power negative 3. Alright, next differentiate minus 2s s squared minus 1 to the power of minus 3. So this one you cannot use chain rule, but you need to use a product rule because this is multiplication of two functions. So let this is u, this is v. So by using product rule, we have u dv plus v du. So u dv, so u is minus 2s, dv is differentiation of v, yeah? Minus 3 times s squared minus 1 minus 3 minus 1 multiply 2s plus v. V is s squared minus 1 minus 3 du. So minus 2s, differentiate, you get minus 2.
So how to get negative 3?
Negative 3. This one from here.
Not negative 1, negative 1 only.
Oh, negative 1. Okay. Sorry, I make some mistake here. Let me change. Thank you. Minus 1, so minus 2, right? So minus 2 here, minus 2 minus 1. Minus 1. Okay. Okay. Anything you can spot? Any wrong? Minus. Okay, here. Minus 2, right? Okay, I think this is correct. Okay, let's continue. So we have, now you need to expand this one. So minus, okay, one more. Here not minus 3, right? Here would be minus 2. Okay. So minus 2 times minus 2, 4. 4 times 2, 8. So 8 s squared. S squared minus 1 to the power of minus 3 plus minus 2 times s squared minus 1 squared. So this one will be 8 s squared over s squared minus 1 to the power of 3 minus 2 over s squared minus 1 square. Okay, so this is our final answer. This is already in simplest form. If you don't like this form, you can combine these two denominator, right? So what you need to do is you need to multiply once again with s squared minus 1 over s squared minus 1. And then you make the denominator equal, and then you expand. But I think no need to expand until that form lah. I think this one is okay. We want to see your last answers. Huh? So I think up to this answer is okay. No need to expand to make your work more difficult. Right, that is the theorem of multiplying by Tn. So any question about this theorem? So far you have seen that we have three theorem, three properties. First properties of Laplace transform is linear properties. Linear properties. So linear properties mean if you have function alpha multiply some function gt plus beta multiply some function ft. So if you want to find a Laplace transform, so by using the linear properties, you can find a Laplace of gt plus beta Laplace of ft. So this is a linear properties. And then you have a properties of first shift properties. First shift properties is about when you multiply by function of exponent at. So you multiply some function exponent at with function t. So what you need to do is first this function ft you transform into fs, and then by applying the properties of exponent at, so you transform this one as equal to s minus a. And last properties is multiplying by Tn. So Tn Ft. So what you need to do is this Ft you transform into Fs, and then by using this property, so negative 1 to the power of n, d to the power of n over dn squared multiplied by differentiation of Fs. So that is the three properties that you need to use. Okay, next is we want to, given that we have function fs, given that you have a function fs, what is a fs? Fs is a Laplace transform function in S domain. So you want to find back what is the original function ft. So what you need to do is you need to apply a inverse Laplace transform. So this is how we write inverse Laplace transform to the power negative 1 of fs. So you transfer back, you inverse back the Laplace transform. So how to find the inverse Laplace transform? The same thing is you need to use the table of Laplace. The same table, but you make it inverse. So let's see this table. So before this, you are given a function in ft. So apply a Laplace transform, you find a function in fs. So now what you have is you have a function in fs. So apply the inverse Laplace transform. So you will get a function in ft. So what we have is on the left column, right column here. So we want to find back what is the function, original function ft. So you use the same table. So in your exam paper later, you will get only one table, this table only. So by using this table, you can find the Laplace and inverse Laplace transform. Based on the table of Laplace, so given that if we have a Laplace fs equal to a over s, So referring the table, A over S is equal to A. For example, if we have Fs equal to 2 over S, then by using the inverse Laplace transform, so inverse of 2 over S is equal to 2. So you look back at the table here. So we have 2 over S. So find the inverse back. This is equal to 2. 10 over S for B. 10 over S. So when you inverse back, you get 10. Okay, based on the Laplace table, Laplace transform, if we have a function n factorial over s to the power f n plus 1, so the inverse Laplace transform is equal to 3 to the power of n. And if you have something multiplied as a numerator to the power of b, so you need to do some modification of this function. So let me explain this one. So first, let's see this example, 1 over s squared. So let's say we have a function fs equal to 1 over s squared. So if we apply a Laplace transform of fs, so I just write 1 over s squared. So this is equal to Laplace inverse Laplace of 1 over s1 plus 1. So in a Laplace table, you found that this one is equal to t to the power of 1. So let's say this is equal to a 1 over s squared. Oh, sorry. 1 over s squared is equal to 2. Is it correct? 1 over s squared. T, yeah? The example is wrong. This one, 1 over s squared. This one is equal to t. Wrong function. 1 over 2 to the power of s3. Okay, B. Let's say we have fs equal to 2 over s to the power of 3. So find ft. So ft is equal to inverse Laplace of 2 to the power of s3. So you can rearrange this one as inverse of 2 over s2 plus 1. 2 to the power of s plus 1. Alright, in a Laplace table, if you look back in a Laplace table, you found that for if we have Tn, this is equal to n factorial over Sn plus 1. So we need to compare this one and this one. So in the numerator, we have n factorial, but here we have 2. So you have 2. So we need to modify this function so that you can use this transformation. So how to modify this function? So first is, because this is 2, so I just can put 2 outside. And then here I have 1. So 2 plus 1. And then here supposed to be 2 factorial, right? in the numerator here, because this is 1, so supposed to be the numerator is 2 factorial. So I need to multiply by 2 factorial and then divide by also 2 factorial. Why? Because 2 factorial divided by 2 factorial, this one is equal to 1. That means I didn't change anything, but I need to modify so that this 2 factorial can go here. And this 2 factorial, it can goes here. So we modify this function so that we have 2 over 2 factorial, a Laplace transform of 2 factorial here as 2 plus 1. So now you can compare this one and this one. So here we have n factorial over s n plus 1. Here we have 2 factorial over 2 plus 1. And this 2 factorial and 2 factorial here can cancel out. So now 2 over 2 factorial is equal to 2 divided by 2 factorial also 2 Laplace transform of 2 factorial over s 2 plus 1. So this one is equal to t to the power of 2. 2 over s 2 over 2 is 1. So multiplied by 1. So this is equal to t square. Okay, let's see question B. 5 over s to the power of 4. So let's say we have fs equal to 5 to the power of s 4. So once again, if I want to compare with Laplace table, if you look at Laplace table, you find that we have this function where the Laplace transform is equal to n factorial over s n plus 1. So I have a Laplace function in this form where the comparison, I think this one, it is just look like this function, kan? Look like this function. So we need to modify this function so that we can rewrite as this one. So first, let's try to modify this one. So we have 5 over s to the power of 4. So let's first put 5 outside. And then here we have 1 over s to the power of, we need n plus 1. So we need 3 plus 1 equal to 4. So here we need to have 3 factorial. So I can short form, I multiply 3 factorial here. And then in order to make it equal to 1 again, here need to divide by 3 factorial. Alright, so a Laplace, inverse Laplace of fs, 5 over 3 factorial. And then we have 3 factorial over s, 3 plus 1. So this is equal to, so we can use the properties of Laplace. So 5 over 3 factorial you can put outside. 5 over 3 factorial. Inverse of 3 factorial over s 3 plus 1. So this one is equal to 3 t to the power of 3. 5 over 3 factorial. So this one is equal to 5 over 6. Okay, can you get it, the concept? I hope you can see how I modified this function. Let's try something more. Another, okay, 4 over 3s7. So let's say we have a function fs equal to 4 over 3 s to the power of 7. Okay, once again, because we only have s to the power of n, so I need to use the properties of this one. T to the power of n equal to n factorial over Sn plus 1. So first, let's modify this function. So first, we put 4 and 3 outside. 4 over 3. Here we have 1 over S7. You need to break down as 6 plus 1. Then close the bracket. So in the numerator, you need to have n factorial. So you need to multiply by 6 factorial. Because if we multiply by 6, we already changed the function. So you need also to divide by 6 factorial. So 6 factorial multiplied by 3. So you get 1 over 540 over 6 factorial s to the power of 6 plus 1. Okay, now you already has this form. This form and this form. So this one will be t to the power of 6. So by using the inverse Laplace of 1 over 4, 540, 6 factorial over s 6 plus 1. So this one is equal to 1 over 6 factorial over s 6 plus 1. So 1 over 540 times t to the power of 6. Let me find one more example. Okay, let's say we have fs equal to 2 over 3 s s3, yeah, 2 to the power 2 over 3 s3. So first, what you need to do is you need to modify this function. So put 2 over 3 outside. Here you have 1 over s2 plus 1. And then because you have 2 plus 1 here, that means you need to multiply by 2 factorial here. And here you need to divide by 2 factorial. So you have 2 over 2 factorial is 2. 2 times 3 is 6. 2 factorial over s2 plus 1. So 1 over 3. So inverse Laplace of 1 over 3 multiply 2 factorial over s2 plus 1. This one is equal to 1 over 3 inverse Laplace of 2 factorial over s2 plus 1. So this one is t squared, so we have 1 over 3 times t squared. Okay, let's move to next example. Okay, let's say we have a function fs equal to 1 over s minus a. So if you look back in the table, 1 over s minus a is actually exponent at. So if we find the inverse Laplace of 1 over s minus a, so you will get exponent at. Now let's say you have b over s minus a. So if we have this one multiplied by b, so like this one, so b over s minus a. So what you need to do is factorize b outside. So you have b and then find the inverse Laplace 1 over s minus a. So this one is exponent at multiplied by b. So you get b exponent at. So for A, example A, Fs equal to 1 over S minus 1. So this one is inverse Laplace of 1 over S minus 1. So this one is exponent T. So referring the table Laplace table, this is exponent A, which is exponent A is minus 1. B, Fs equal to 1 over S plus 3. So inverse Laplace of 1 over S plus 3. So this one is equal to exponent minus 3t. So by looking a table, so this one is exponent 3t. 2 over s minus 4. So we have fs equal to 2 over s minus 4. So inverse Laplace of 2 over s minus 4. So you can put 2 outside. And then we have 1 over s minus 4. So 1 over s minus 4 is exponent 4t. So times 2, 2 exponent 4t. 3 over s plus 2. Fs equal to 3 over s plus 2. So find ft. So inverse Laplace of 3 over s plus 2. So 3 you can put outside. So 1 over s plus 2. So this one is equal to exponent 2t. So multiply by 3. So we get 3 exponent minus 2t. Sorry. 3 exponent minus 2t. Okay, now let's see another function. So if a Laplace equal to a over s squared plus a squared. Let me check here. So now let's say we have a over s squared plus a squared. A is a number, a constant. So this is a constant. Here we have a, here we have a squared. Make sure you have the same constant, a here and a here. So by using this Laplace table, so this one is equal to sine at. And normally, sometimes you don't have a same number in the numerator. Here you have a, so this applied as equal to sine at. But if we have b, so what you need to do is this b, first you need to move outside. So you have b here, and then a Laplace of, so if you take b outside, here will be 1. So you have 1 over s squared plus a squared. Now we want to use this function. So because here you need to have a, what you need to do is you multiply by a. And then you also divide by a. Why? Because a over a doesn't change this function. A over a actually is 1. So now a can be here. This a can be here. So we have b over a, Laplace inverse Laplace of a over s squared plus a squared. So the answer will be b over a, b over a sine 80. Okay, let's check this one. So we have fs equal to 1 over s squared plus 1. So we have here a, here also a. This one supposed to be 1 to the power of 2, a to the power of 2. Here is a to the power of 1. So 1 squared is also 1. So here you have an inverse Laplace of 1 over s squared plus 1 squared. So this one is equal to sine t. Okay, here, this one also can be rewrite as 2 over s squared plus 2 squared. So you have a same numerator, a and a squared. So this one is easy, yeah? So Laplace of 2 over s squared plus 2 squared. So this one is sine 2t. So okay, let's see this one. 2 over 3s squared plus 27. So we have fs equal to 2 over 3s squared plus 27. Okay, so we would like to use the fact that if we have a over s squared plus a squared, this is equal to sine 80. So if we observe our function, this one, the coefficient of s squared must be equal to 1. Here we have 3. So we need to factor this one, 3 and 27, you can factor outside. So first we have 2 over 3, I can put outside. So now inside will be s squared plus 9. When 9 actually is 3 to the power of 2, right? So we have 2 over 3 multiplied s squared plus 3 squared. Okay, so we are going to use this information. So find an inverse Laplace of 2 over 3 multiplied s squared plus 3 squared. So 2 over 3 is a constant, so I can put this constant outside. And then I have inverse Laplace of 1 over s squared plus 3 squared. So here I need to have 3, yeah? In the numerator here, this one, I need to have same with this one. Here I have 1, here I have 3. So I need to multiply by 3 and divide by 3. So we need to multiply by 3 here and then divide by 3. So this 3 you can put here. So we have 2 over 3 times 3 is 9. So this one will be sine 3t. So the answer is 2 over 9 sine 3t. So you need to modify a function so that your function is actually you can find in the Laplace table. So we have 2 over 9 sine 3t. Okay, now let's see another function. Just now we have a constant upside. In the numerator, you have a constant just now. Now you have a function s, a variable s. So by referring the table, if we have s over s squared plus a squared, so this one you can obtain from the table. This one is equal to cos at. But normally or sometimes you don't have s here. Maybe you have some function, let's say b multiply s, like this one. So b multiply s. So you want to use this one so that this function resemble this one. So what you need to do is, if you have b times s, so this b, because this is a constant, so you can put outside. So you put b outside, and then s over s squared plus a squared. So the answer will be b times cos at. Right, so this one actually you need to rewrite as s over s squared plus 2 squared. So inverse Laplace of s over s squared plus 2 squared. So this one is cos 2t. 2s over s squared plus 3. So we have 2s over s squared plus 3. So we need to rewrite this one as 2s over s squared plus, here supposed to be a squared. You have 3. That means this one is square root 3 to the power of 2. If you take square root and you square this one, you get 3. So inverse Laplace of 2s over s squared plus square root of 3 squared. So this one, you need to, this constant 2, you need to move outside. So you can rewrite as 2 inverse of Laplace s over s squared plus root of 3 squared. So we have 2 cos a. Yeah? So a is root of 3 times t. So 2 cos root of square root 3. S over 4s squared plus 16. So we have fs equal to s over 4s squared plus 16. S over 4s squared plus 16. So we need to use this table, s over s squared plus a squared. So here you have a coefficient in front of s squared. So you need to make this one equal to 1. So you need to factor 4. So 4 outside. So you have s squared plus 4 inside. 4 times 4 is 16. 4 inside also can be rewrite as 2 square. So s over 4 s square plus 2. So inverse Laplace of this function, 4 over s square plus 2 square. So this 4 you can put outside. So we have 1 over 4 inverse Laplace of s over s square plus 2 square. So we have 1 over 4 cos 2t. One over 4 cos plus 2t. Alright, so next function, if we have this one, a over s squared minus a squared. So if you look at the table, you can find this function. So the inverse Laplace equal to sine 80. The things that you make sure is you have a same a and a here. So this one should be a squared, this one should be a. So now the problem is here in the numerator you have not equal to a. For example, you have b, like this one. So we need to modify this one so that it can be equal to this one. So first, you need to move b outside. So let's rewrite as b. Inverse Laplace of 1 over s squared minus a squared. So now we want this one equal to a. So you multiply by a and divide by a. So this one goes here, this one goes here. So you have b over a over s squared minus a squared. So you have, what is this? You have b over a sine 80. Okay, for example, this one. Fs equal to 4 over s squared minus 16. So you can just rewrite as 4 over s squared minus 4 squared. So inverse Laplace of this function. So you have sine 40. Make sure that you have this numerator a and this one is a square. If you observe this one and this one are equal, then just rewrite the formula. Three over s square minus 49. Three over s square minus 49. So inverse Laplace of 3 over s square minus 49. So 49 is 7 square. Okay, you can rewrite as this one. Now, because we don't have a same coefficient here, here is 7, but here is 3. So this 3, you need to move outside. So this one is equal to 3 multiply inverse Laplace of, here is 1, because you move 3 outside. So you have s squared minus 7 squared. You want the numerator equal to 7. Here you want equal to 7. So you multiply by 7 here. Here you divide by 7. So now you have 3 over 7. Here is sine 7t. Alright, next one, s over s squared minus a squared. So this one you can obtain directly from table. This one equal to cos 80. So cos 80. So the same thing is, what happen if we don't have s here, but you have some constant or some number multiplied by s. For example, b multiplied by s. So same thing, move b outside, and then inside you have s over s squared minus a squared. If you have something here, for example, you have 4s, so you need to make sure that this one only s, the coefficient must be only 1. So this one also you can move outside, put outside. So as this equation, so you need to rewrite as a Laplace of s over s squared minus, here supposed to be a squared, but we have 5. That means here we have square root of 5 square. So here we have cos square root of 5t. Cos. So cos square root of 5t. Two s over s squared minus 100. Two s over s squared minus 100. So inverse Laplace of 2s over s squared minus 100. 100 is 10 square. So we want only s here. So 2 you can put outside. So we have 2 inverse Laplace of s over s squared minus 10 square. So you have 2 times cos 10t. Right. We continue our lesson. So next is the properties of inverse Laplace transform. Just like the properties of Laplace transform, where we have 3 properties, the inverse Laplace transform, we also has 3 properties. So for inverse Laplace transform, so we will have 3 properties also. First is a linear property, just like a Laplace transform. And then second, we have first shift property. First shift property. This is a properties regarding the exponent at. And lastly, we have a properties regarding a rational function. So before we end our class later, I need you to read. Please read about the rational function. So this one, you need to know what is a rational function, how to obtain a rational function from improper function, and then how to obtain the coefficient for rational function. So you need to read about this, or you can find from the books, or you can find from the internet how to get a rational function. Because in the in the next class, I will not discuss how to obtain a rational function. Rather than I will just discuss the method and how we want to use these properties. All right, so I want to continue with the first properties, which is a linear properties of Laplace transform. So as I said just now, we have three properties which apply to use inverse Laplace transform. Because not all functions in a Laplace domain you can transform directly to ft. So you need to apply these three properties. That means you need to know and you need to make sure you understand all these three properties in order to use a inverse Laplace transform. So we have a linear properties, we have first shift properties, and we also have a rational function. And all of these properties, you will use the same table. We will referring the same table. So let's see the first one. The first properties of inverse Laplace transform we call a linear property. If a inverse Laplace of Fs is equal to Ft and inverse Laplace of Gs equal to Gt, alpha and beta are constant, then a sum function multiply Fs, sum constant alpha multiply Fs, sum constant beta multiply Gs. So what you need to do is we can put alpha outside and then you find the inverse of Fs. So inverse of Fs is Ft. So alpha multiply Ft, you get alpha Ft. Same goes to bis beta. So beta you can put outside. So put a beta outside multiplied by inverse of Laplace Gs, where the inverse of Gs is Gt. So beta times Gt. So that is the linear properties of inverse Laplace transform. And then let's see this problem. Find or apply a linear property of inverse Laplace transform to find Ft. So we want to find the Ft. So we are given Fs, which is Fs is a inverse, Fs is a Laplace transform. You have a function in S. So we want to transform this into Ft. So you need to apply all these properties. So first property, we have a linear properties. Fs equal to 2 over S plus 4 over S plus 1. So number one, change the color, let's say. So number one, we have 2 over S. So this is Fs. Let me rewrite then. Fs equal to 2 over S plus 4 over S plus 1. So now we need to use these properties of Laplace. So inverse of Laplace 2 over S plus 4 over S plus 1. So this is equal to inverse of 2 over S plus inverse of 4 over S plus 1. And then this 2 is a constant, because if you look at a Laplace table, this one actually you can find from the Laplace table. We have A equal to Ft equal to A, Fs equal to A over S. And this one, we have exponent At equal to balik so exponent at. So this one equal to 1 over s plus 1. Balik. Exponent at equal to 1 over s minus a. Alright, so we have 2 over s, so I can put 2 outside. And then here I have 1 over s. So now I can use these properties. And then I have 4 outside. So 1 over s plus 1. So 1 over s is 1. So this one equal to 1. So 2 times 1 is 2 plus 4. Here is s minus a equal to exponent at. Here s plus 1. So a is minus 1. So here we have 4 exponent minus t. Number 2. 3 over s squared minus 2 over s6 minus 2 over s6. Right, so let's find the inverse of this function. 3 over s squared minus 2 over s6. So I can rewrite by using linear properties. So here will be 3 over s squared minus inverse of 2 over s6. Three is a constant, so I can put outside. Here I have 1 because I pull 3 outside. So here I have 1 over s, 1 plus 1. Minus 2 I can put outside. 3 to the power s squared, s cubed, sorry. 3 to the power of s cubed. S cubed, so we have s cubed here, here we have s cubed. So here we have, so let me rewrite this one. So here s cubed, so s2 plus 1. So now not finished yet. So here, because I have 2 here, here I need to have 2 factorial, right? In order to use a table, because we have t to the power of n equal to n factorial s n plus 1. So if I want to use this formula, here I need to have 2 factorial. So what I need to do is I multiply by 2 factorial here. Here I divide by 2 factorial. Alright, continue. Here I have 2 outside. Inverse of, here will be 1. S to the power of 5 plus 1. So same thing also. Here we have 5. So up here I need to multiply by 5 factorial. Because I multiply 5 factorial, I need to divide outside also by 5 factorial. So 3 over 2 factorial is 3 over 2. Here will be t to the power of 2, right? So here will be t squared. 2 over 5 factorial is 1 over 60. So use your calculator, 1 over 60. Here will be t to the power of 5. So 3 over 2 t squared minus 1 over 60 t to the power of 5. So that is question number 2. Question number 3, Fs equal to, okay, here. Question number 3, Fs equal to 6s minus 7 over s to the power of 4. To the power of s to the power of 4. Alright, so if you look at the Laplace table, we cannot find any function or any function that resemble like this function. Any closed function, you don't find any formula that equal to this function. So you need to rearrange because you only have two things. You only have if the denominator equal to s to the power of n. The closed one that you can find is only if we have t to the power of n, this is equal to n factorial over s n plus 1. Only this one is the close one to this one, because you only have a denominator equal to s to the power of 4. So this one, I think, or I suspected, this one is about t to the power of n. So you need to modify this function, rearrange, so that you can rewrite as this one. Okay, now let's try to rewrite this one. You can break this equation or this fraction as 6s over s to the power of 4 minus 7 over s to the power of 4. So this function, we can break down as this one, this fraction. 6s to the power, 6s over s to the power of 4. Here we have s, so you can cross. Here s to the power of 4, so here will be s to the power of 3. So here you should have 6 over s cubed minus 7 over s to the power of 4. Now it resembles like t to the power of n. So you need to rearrange so that you can find n factorial here. Here's supposed to be 2 plus 1. Here's supposed to be 3 plus 1. Alright, so by using this information, now let's rewrite as inverse Laplace of 6 over s cubed minus 7 over s to the power of 4. So linear properties, you can divide or you can break down this into two equations. So put 6 outside, inverse Laplace of 1 over s to the power of 2 plus 1 minus, now 7 I can put outside. So here I have inverse of 1 over 4 is 3 plus 1. Okay, so now I have this one. So here I need to have 2 factorial. So I need to multiply by, let's change the color. So I need to multiply by 2 factorial. Here divide by 2 factorial. While here I need to multiply by 3 factorial and divide by 3 factorial here. So 2 factorial is 2, 6 divided by 2 is 3. Here will be t to the power of 2 or t square. So 3t square 3 factorial is 6. 3 factorial is 6. So 7 over 6 t to the power of 3. So that is our answer. Okay, two more. Question number 4. S plus 2 over S squared plus 9. Question number 4. Fs equal to S plus 2 over S squared plus 9. So the closest function that I can find is if we have, let me change the color. So if I have cos AT, this is equal to S over S squared plus A squared. Sin AT, this is equal to A over S squared plus A squared. Because the denominator is S squared plus A squared. Here I found that this one close to these two function. But here I have S plus 2. Here only S, here only A. So this function or this fraction, we can break down into two function or two fraction. First fraction, we have S over S squared plus 9. 9 is 3 squared. Another one is 2 over S squared plus 3 squared. If you add these two functions, you will get the original one. Right, so now by using this information, here I can write as S over S squared plus 3 squared. Sorry. Plus 2 over S squared plus 3 squared. So now let's break down one by one. So here would be inverse of S over S squared plus 3 squared. Plus 2 is a number, so you can put outside. So put outside 2. Here I have 1 over S squared plus 3 squared. Why I put this 2 outside? If this is not 2 but 3, then I just can use this formula. But now here is 2, not equal to this one. Here is A, here is B. So not equal, so we need to put B outside. So because I want here to be 3, so I multiply by 3 here. Here I divide by 3. So now here you have this function to be cos 3t. And this one will be sin 3t. So sin 3t over times 2 over 3. So here we have cos 3t plus 2 over 3 sin 3t. At number 5, fs equal to 2s minus 3 over s squared minus 25. S squared minus 25. Okay, let me rewrite this one again. So if we have minus here, so we could have either cos 80, this one equal to s over s squared minus a squared, or sin 80, this one should be a over s squared minus a squared. Observe the denominator first before you determine what table you need to use. Okay, now we have 2s, so you need to break down 2s and 3. So here, let's break down this fraction as 2s over s square minus 25 is 5 square minus 3 over s square minus 5 square. And now this one should be sine, this one should be cos. So inverse Laplace of 2s over s square minus 5 square minus 3 over s square minus 5 square. So by using linear properties, I can put 2 outside. Inverse of s over s square minus 5 square. And then because 3 and 5 are not equal numbers, so these 3 I can put outside. So minus 3 inverse of 1 over s square minus 5 square. Okay, so here I need to have 5 in the numerator, so here I need to divide by 5. So I have 2, this one is cos 5t. Here 3 minus 3 over 5 sine 5t. All right. Okay, so that's cover the first properties of inverse, which is linear properties of the inverse. So before we stop our classes, as usual, I will give you the example or the exercise. I need you to do this exercise and submit to me. So I will send this exercise by using our WhatsApp group because some of your friends are not attending these classes. So I will give this exercise using our WhatsApp group. So with that, I think if you have any question, ada tak soalan? Okay, kalau tak ada soalan, I think we will dismiss our classes. Thank you for joining us. Next Monday, once again, no classes, right? Kan? Okay, next Monday, holiday. So I think that's all for today. Thank you. Assalamualaikum. Good night. Bye.
Thank you,
Thank you,
Doctor.
Doctor.
Thank you,
Thank you,
Doctor.
Thank you,
sir.
Doctor.
Thank you.
Thank you,
Bye.
sir.
Bye.